2.3, the product rule. We're going to develop a rule for differentiating the product of two functions. So what this would look like is, we have examples here such as f at x equals, we would have the product of 3x squared minus 1 times x cubed plus 8. Or for g at x, we have another example. We have x minus 3 cubed times x plus 2 squared. So we can see that we have one function here and then multiplied by another function. And then for g at x, the same thing. We have a function multiplied by another function. Okay, so we're going to show in investigation that the product of individually of two functions is not the product of an overall function when multiplied. Okay, so investigation. Let p at x equals f at x times g at x. Okay, so our p at x is going to be two functions multiplied by one another. So we have the function f at x equals x squared plus 1. So let's go ahead and I'll write this out down here. So for f at x, we have x squared plus 1. And for g at x, we have x plus 5. What we're going to do is we're going to show that the derivative of p at x, which I just set up the formula for p at x, does not equal the derivative of its parts. Okay, so let's find the derivative of p at x first. First, what we're going to do is we're going to expand f at x times g at x. Okay, so x squared times x is x cubed. X squared times 5 is 5x squared. 1 times x is x, and 1 times 5 is 5. Now, this is p at x. None of these are like terms, so this is fully expanded. So when I do the derivative of p at x, so p prime at x, this 3 comes down, and we get 3x, and we subtract 1 in the exponent, so we get 2. Plus, this 2 comes down, multiplies by the 5, we get 10x, and then subtract 1 from the exponent, we get 10x to the exponent 1. So I'm not going to write that in there. And then we have the term 1x, and this is technically to the exponent 1. So if we took this 1 and we multiplied it by 1, we're going to get 1. But then if we subtract 1 from the exponent and we get 0, any number to the 0 is just 1. So 1 times 1 is 1. So as a short form, the derivative of x, or any coefficient x, is just going to be that coefficient. Okay, and the derivative of the constant 5 is just 0. So this is our actual derivative of p at x. Now what we're going to take a look at is this part of the equation. Okay, so we have f prime at x times g prime at x. And we're going to show that these two are not equal. So going back up here, if we took f at x and we solve for x prime at x of x squared plus 1, we would take this 2 in the front of the x, subtract 1, and we just get 2x, right? The derivative of a constant is nothing, so that just goes away. Now, g at x, if we wanted to solve for g prime at x, if we have x to the exponent 1, all we do is we take the coefficient. So 1. And then the derivative of 5 is 0, so we have 1. So subbing these in, we would have 2x times 1, which is just 2x. Okay, and that is f prime at x times g prime at x. As we can see, when we compare these two, p prime at x does not equal f prime at x times g prime at x, because we can see that 3x squared plus 10x plus 1 does not equal 2x. So the whole purpose of the product rule, which we're going to get into, is that we cannot just find the derivative of each of the functions and multiply them because it doesn't work. Okay, the product rule. The derivative of the product of two functions is equal to the derivative of the first function times the second function plus the first function times the derivative of the second function. In other words, if we have p at x equals, and then we have two functions, f at x and g at x, what ends up happening when we find the derivative p prime at x is we find the derivative of the first function multiplied by the original second function, and then plus the first function times the derivative of the second function. Okay? In Leibniz notation, a lot of times u and v are used. You'll see this a lot in university. So if u and v are functions of x, how we'd write this is the derivative d by dx of uv, right? Without this extra variable here, it's telling us we're going to find the derivative of uv. So u is a function, v is a function, u times v. It's going to be the derivative of the first function times the second plus the first times the derivative of the second. Okay, let's go. Example 2. Differentiate h at x equals, and then we have two functions. We have x squared minus 3x, and then we have x to the 5 plus 2 using the product rule. So at this point, we're not going to expand these. What we're going to do, so let's call this one f at x, and let's call this one g at x, just for simplicity. So if we took f at x equals x squared minus 3x, then we can talk about f prime at x equals, we would bring this 2 down and we'd have 2x, right, to the 1. And then negative 3x to the 1. Because it's x to the 1, we just take the coefficient. Okay, and if we called this one g at x, and we have x to the 5 plus 2, then g prime at x equals, bring the 5 down, x. When we subtract 1 from the exponent, we get 4. And then the derivative of a constant is just 0. So that's what we get. Okay, so putting this all together, if we want to write out the actual product rule, we can say p prime at x equals f prime at x, g at x, plus f at x, g prime at x. So, in other words, when we find the derivative, oh, I put p, this is an h, because we're dealing with h at x. Okay, so f prime at x, so the derivative of the first one, which is 2x minus 3, times the second equation as it is, so x to the 5 plus 2, plus f at x, which is the original, which is x squared minus 3x, times the derivative of the second function, which is 5x to the 4. Okay, so at this point, our differentiation is done, and we can just expand and simplify. So we can do 2x times x to the 5, which is 2x to the 6, 2x times 2, which is 4x, negative 3 times x to the 5 is negative 3x to the 5, and negative 3 times 2 is negative 6. Plus, okay, so this is a monomial, so we only have to multiply, and I'll do this a little bit backwards, 5x to the 4 times x squared, so we have 5x to the 6, minus 15x to the 5. And then if we collect like terms, we get 7x to the 6, negative 3 and negative 15, so I get negative 18x to the 5, plus 4x, and then minus 6. And this is the expanded version of f prime at x. Okay, when asked to evaluate a derivative at a certain value for x, differentiate first, so that means just find the derivative first, then sub in the value to evaluate. Okay, so example 3, find the value h prime at -1 for the function h at x equals, and then we have the product of two functions here. 5x cubed plus 7x squared plus 3, and then 2x squared plus x plus 6. So let's go ahead and call this one f at x, and let's go ahead and call this one g at x. Okay, so let's set this up. I'm going to go f at x equals, and then f prime at x equals. Okay, and I'm going to set this up as 5x cubed plus 7x squared plus 3. Now, for f prime at x, I'm going to bring the 3 down. 3 times 5 is 15, x, and then we subtract 1 from the exponent, so I get x squared. Plus, bring down that 2. 7 times 2 is 14, x, and then subtract 1 from the exponent, and we get 1. I'm not going to include that. Okay, and then plus 3. 3 is a constant, so derivative of 3 is 0. Here is our f prime at x. Now I'm going to set this up the same way, g at x and then g prime at x. So g at x is going to be 2x squared plus x plus 6. Okay, the original. Now g prime at x, I'm going to multiply 2 by 2 and we get 4x. When we subtract 1, we get to the exponent 1. I'm not going to include that exponent. And the derivative of x is just going to be the coefficient, so plus 1. The derivative of a constant is nothing, like 0, so we leave that out. Okay. And now we can do the derivative. H prime at x is going to equal the derivative of the first function times the second function plus the first function times the derivative of the second function. So we get f prime at x, 15x squared plus 14x, and then times g at x, which is 2x squared plus x plus 6, plus f at x, which is the original, 5x cubed plus 7x squared plus 3, and then times g prime at x, which is 4x plus 1. Okay, so right here, this is our actual derivative. So at this point, I'm not going to FOIL or expand this because we know that we're going to sub in h prime at -1. So it's not going to make a difference if we expand it. I think it's easy enough to sub in the -1 and evaluate as is. All right, so this is going to be 15 times -1 squared plus 14 times -1. This is going to be 2 times -1 squared plus -1 plus 6. Plus, we're going to go 5 times -1 cubed plus 7 times -1 squared plus 3. And then 4 times -1 plus 1. Okay, so when I'm looking at this, I go, -1 squared is just 1, so I get 15. 14 times -1 minus 14. And that's it for the first bracket. Second bracket, -1 squared is just 1, so I get 2 plus -1, so -1 plus 6. Okay, -1 cubed is still -1, so I get -5. -1 squared is 1, so I get plus 7, and then plus 3. And then this is -4 plus 1. All right, so 15 minus 14 is just 1. So it's going to be 1 times whatever this is. So I'm not even going to include that. And then 2 minus 1 is 1, plus 6 is 7. Okay, now -5 plus 7 is 2, plus 3 is 5, times -4 plus 1 is -3. So I get 7 plus -8, I get -1. Sorry, these were multiplied. This is minus 15. So 7 minus 15 is -8. Okay, so we can say h prime at -1 equals -8. That means the slope of h at x at the point -1 is -8. Okay, example 4, we're going to find an expression for p prime at x, but in this case, p at x equals f at x, g at x, h at x. So we no longer only have two functions that are multiplied by one another. We now have three functions that are multiplied by one another. So what I'm going to do is I'm going to group f at x and g at x, and I'm going to use the product rule. And I'm going to use the product rule inside of a product rule. So we're going to go p prime at x, and we're going to go, so just remember, we're doing, you know what, I'm going to use u and v this time, u and v. So the short form for the uv is u prime v plus uv prime. Okay, so the derivative of f at x, g at x, right, because that's going to be u, the derivative of that entire thing is going to be the product rule in itself. F prime at x, g at x, plus f at x, g prime at x. So that's the derivative of u. Now we're going to multiply by v, so times h at x. Now, what is u as it is? That's simply f at x, g at x. And now what is the derivative of v? Well, that's just h prime at x. So we can go ahead and distribute this h at x, and we're going to get f prime at x, g at x, h at x, and then f at x, g prime at x, h at x, and then plus f at x, g at x, h prime at x. So if we actually take a look at this and we look at the pattern, we have the derivative of the first times the second times the third. Then we have the derivative of the second times the first times the third. Then we have the derivative of the third times the first times the second, as they are. Okay, so this is p prime at x. Now we're going to do the power of a function rule for positive integers. So the power of a function rule is a special case of the chain rule. Okay, so I'm going to teach this right now. If u is a function of x and n is an integer, then the derivative, d by dx, of u to the n equals, well, we already know we bring down the n to multiply by u, and then we subtract 1 in the exponent. So we already know that. Now what ends up happening is when this u is not just simply an x, but when we have a full function, we actually have to take du by dx. We have to take the derivative of u with respect to x. Okay? If we want to look at this not in Leibniz notation, but in function notation, okay, we can say if f at x equals some function g at x to the exponent n, then we still bring down that n, and f prime at x, so the derivative of f at x equals n, that got brought down in front. We write the function as it is, so that doesn't change. We subtract 1 in the exponent, and then we multiply it by the derivative of what's inside that function. Okay, so let's do this hands-on. For h at x equals x squared plus 3x plus 5 to the exponent 6, we're going to find h prime at x. So far what we've done is we've brought this 6 down, and we've had h prime at x equals 6, and we're going to write this as it is, x squared plus 3x plus 5. And then we're going to subtract 1 from the exponent, and we get exponent 5. So this is what we've done so far with the power rule. okay, differentiating when we have a power. Now, this is going to be a little bit different. We have to multiply now by the derivative of what's inside this bracket. So this 2 will come down and we get 2x. And for 3x, we lose the x and we take the coefficient, so plus 3. Okay, derivative of 5 is 0, so that goes away as well. So our derivative is this entire thing, 6, bracket the original, x squared plus 3x plus 5 to the exponent 5, which is down 1 degree, and then the derivative of what's inside the bracket, that function, 2x plus 3. So what we did here, just so that we can see it with Leibniz notation, okay? So we know that we bring down the 6, we write this, and then the exponent 5. What we actually did here is we did d by dx of the original x squared plus 3x plus 5. This is what we did here. Okay, example 6, differentiate the rational function f at x equals 2x plus 5 over 3x minus 1. Okay, we actually haven't done quotient rule yet, or quotient rule. But what we're going to do is we're going to first rewrite this expression as the product of two functions, and then we're going to use the product rule. Okay, so let's rewrite this. I get f at x equals, the numerator is going to be normal, 2x plus 5. But instead of dividing by 3x minus 1, I'm going to bring this 3x minus 1 up to the numerator, and I'm going to raise it to the exponent negative 1. So now we have the product rule. And if this function is u and this function is v, then we know the derivative of f at x is going to be u prime v plus uv prime. Okay, so instead of writing the derivative of f at x, just so that we have this here, I'm going to write uv prime. So the derivative of u times v, because that's what I'm going to call it up here. So this is just kind of like an aside, okay? So let's go ahead and let's differentiate. So we have f prime at x. Okay, so what we're going to do is we are going to find the derivative of u. So we're going to go d by dx of 2x plus 5. Okay, then we're going to multiply by v. So we're just going to write out 3x minus 1 to the negative 1. Then we're going to add u as it is, so 2x plus 5. And then we're going to multiply by v prime. So we're going to do d by dx of 3x minus 1. Okay, and don't forget, d by dx is telling us we need to differentiate what's beside it. Okay, so if we differentiated 2x plus 5, we're going to get the constant 2. And then we can just bring this down, 3x minus 1 to the negative 1. Then we have 2x plus 5 here. So let's rewrite this, 2x plus 5. And then d by dx is telling us we need to differentiate 3x minus 1. Oh, sorry, that's to the negative 1. So in order to differentiate this, we have to use that chain rule. So we're going to bring negative 1 in front. So this is going to be times negative 1. We're going to write the bracket as it is, 3x minus 1. We're going to subtract 1 from the exponent, which is negative 2. And then what we have to do is we have to do the derivative of what's inside that bracket, which is 3x minus 1. So I'm going to rewrite all of this, and then I'm going to go ahead and derive 3x minus 1. So we have 3x minus 1 to the negative 1 plus 2x plus 5 times -1 times 3x minus 1 to the -2. And then the derivative of 3x minus 1 is just 3. So if this question said differentiate using the product rule and that's it, then you don't have to simplify, and this line is your derivative. Also, if you're subbing a value in for x, I wouldn't go further than this. I would just find the derivative, sub in right away, okay? Because then what you're doing is you're risking that you're going to make mistakes doing the computation, okay? But I'm going to show you how to actually simplify this. And so I'm going to go ahead and rewrite this. So I have 2 times 3x minus 1 to the -1. Because I have the exponent of -1, what I'm going to do is I'm going to rewrite this as 2 over 3x minus 1. Actually, I'm going to factor this. I'm going to write this fully factored. It's more common. Okay. At the side of your paper, you might want to write this little cheat sheet. You might want to say divide by the lowest exponent. Okay. So first what I'm going to do is I'm going to rewrite 2 bracket 3x minus 1 to the -1. All I'm going to do in the second part here is I'm going to multiply this -1 and this 3. Just put them together. So -3 bracket 2x plus 5 bracket 3x minus 1 to the -2. Okay, so what is going to be identical between this term here and this term here? Well, the 3x minus 1. The difficult part of this is to decide which exponent am I going to divide it by. Am I going to divide it by -1 or am I going to divide it by 2? Well, I'm going to divide it by, -2, because that is the lower exponent. It's a lower number. Okay, so our common factor is 3x minus 1 to the -2. And then what do we have left? Okay, if you think about exponent laws, when we divide two numbers with the same base, so in this case, our base is going to be 3x minus 1. What we do is we subtract the exponents. So this exponent, -1, we would subtract -1 minus -2. And then what do we get? So -1 minus -2 actually gives us 1. So 3x minus 1, so the exponent 1 is left. Oh, 2. Sorry, I forgot. There's 2 in front. 2. And then 3x minus 1 is going to be left in the first term. Then in the second term, so this and this cancel because we factored this out. So now it's -3, 2x plus 5. Okay. I really like this because now everything in this bracket has a positive exponent and we don't have fractions. We have this is kind of a fraction here, 3x minus 1 to the -2. It definitely is. But that's one of our factors. So this is already factored out, so we can just leave it. And now what I would do is I would distribute in and simplify. So 2 times 3x is 6x, 2 times -1 is -2, -3 times 2x is -6x, -3 times 5 is -15. And then I'm going to change these to round brackets now because this is going to be our other factor. So 6x minus 6x goes away and I get -17. So to rewrite this, I would put -17 bracket 3x minus 1 to the -2, or you could put -17 over 3x minus 1 squared. And that's fully factored, fully simplified. Example 7, the position S in centimeters of an object moving in a straight line is given by this equation. where t is greater than or equal to 0, okay, and where t is the time in seconds. So this makes sense for the domain. Usually time is greater than 0 because we can't go back in time. We can only start to log the time from, say, for example, now, okay? And t is the time in seconds. Determine the object's velocity at t equals 2. Okay, so when we talk about velocity, I want to say this. So S is usually denotes the displacement. Okay, if we find S prime, what this denotes is actually velocity. So velocity. And if we take the derivative of v, so v prime, or S double prime, and we're going to study this later, but the second derivative is going to be the first derivative of velocity. This is actually going to be a, and this is acceleration. Okay, so when you see S, usually this is displacement. So we have this function. This function, I'm just going to rewrite it. This function is definitely product rule. So we have S equals t times 6 minus 3t to the exponent 4. Okay, so this is, for example, u, this is v. So as a reminder, the derivative of uv is derivative of u times v plus u times the derivative of v. This is our product rule. All right, so S prime, which actually also means velocity, is derivative of the first function. So what's the derivative of t? It's just 1. You know, I'm going to write out d by dt. We'll write out what we're actually going to do first. Okay, d by dt of t, right? The derivative of the first function, then times the second function as it is. So 6 minus 3t to the exponent 4. And then we have plus u as it is, so that's just t, times the derivative of v. So we're going to have d by dt, and then of 6 minus 3t to the exponent 4. And remember, these are now d by dt because we have a function of s written with respect to t. So the derivative of the displacement, which actually means the velocity, okay, so d by dt of t, well, the derivative of t is just 1, and then times 6 minus 3t to the 4, okay, plus t as it is times the derivative of 6 minus 3t to the exponent 4. So what we're going to do here is we're going to bring down the 4. Okay, we're going to subtract 1 from the 4, so 6 minus 3t to the exponent 3. And then we have to differentiate what's in that bracket, so 6 minus 3t. So in the next line, we're going to get S prime equals V equals. So I'm no longer going to write this 1 here. I'm just going to write 6 minus 3t to the exponent 4. T times 4, I'm actually going to write as 4t. And then 6 minus 3t to the exponent 3. And now we're going to differentiate 6 minus 3t. So this is not written in standard form. Usually it's written negative 3t plus 6, but that's okay. The derivative, we're going to do the derivative of 6 minus 3, and then the derivative of t, right? Minus 3t. So the derivative of 6 is just a constant, like this 6 is a constant, so it's just 0. That goes away. And the derivative of negative 3 d by dt t. So the derivative of t is just 1. So that goes away and we just get negative 3. But all of this was multiplied. So S prime equals V equals, and then I'm just going to rewrite this one more time, but I'm going to multiply the 4t and the negative 3. Okay, so 6 minus 3t to the 4 minus 12t, 6 minus 3t to the 3. So I'm going to write this in factored form just for practice, but usually I wouldn't because this question asks, determine the object's velocity at t equals 2. So at this point here, without even simplifying much, we could sub in t equals 2. But I'm going to write this in factored form just for practice, okay? So our rule is that we're going to divide by the lowest exponent. So what's similar in these two terms? What's identical? 6 minus 3t. And what exponent is smaller, 4 or 3? Well, 3 is smaller. So we're going to go ahead and factor out the 3. So I get S prime equals, or V equals. So our common factor is 6 minus 3t to the 3. Okay. Then in big brackets, 4 minus 3, that would cancel to a 1. So we still have 6 minus 3t. And then we have 6 minus 3t to the cubed. Those can cancel out, so we're left with minus 12t. So simplifying this bracket, we're going to have our factor, 6 minus 3t to the 3. And then we're going to have 6 minus 3t minus 12t, which is just 6 minus 15t. So this is fully factored, fully simplified. Okay. Now, we can go ahead and sub in S prime at 2 or the velocity at 2 seconds. So 6 minus 3 times 2. And that's all raised to the exponent 3 times 6 minus 15 times 2. Okay, so I get 6 minus 6 cubed, and then 6 minus 30. But 6 minus 6 is just 0. So 0 to the exponent of anything is 0, times anything is 0. So I get the object is not moving, so it's at rest. Okay, so I'm going to write at rest because that's a very popular math term. Okay, at t equals 2 seconds.